Okay, folks, do you drive a Hemi? Well, I know that's a weird question to ask you in organic, but we're getting ready to talk about Hemis. And we need to figure out what a Hemi is in organic chemistry. All right, so we just finished talking about the reaction of an aldehyde or a ketone. So here we'll do R or an H with something like water. So we treated this like H and OH. OH goes on to the carbon and the hydrogen goes on to the oxygen that's already there, giving us two OH groups. And those two OH groups were called Gemini twins, and we called them gem-diols because of that. All right, well, that's great. However, in this video, I told you that instead of water, we were going to look at things like alcohols. This was something that was done in Chemistry 251. A reaction of an alcohol onto a double bond. The double bond breaks, hydrogen goes on one, and the OCH3 goes on to the other. So this time we're going to take an aldehyde or a ketone, and we are going to react it with an alcohol. Now, the alcohol is going to require a catalyst, folks, and the catalyst is going to be a little bit of proton. So a little bit of proton goes a long, long way. So a little bit of hydrogen will come in and basically jumpstart and initiate this reaction. So we've got a carbon double bond O and a random carbon chain to the left and maybe a random carbon chain to the right or a hydrogen. So what's going to go on? What's going to happen? The same thing as kind of before. So CH3OH, split it up, beep, two parts, hydrogen and OCH3. Those are our two pieces, just like H and the OH that was prior. So the nucleophile, the negative containing piece, is the OCH3, and the OCH3 is going to go there. Well, when that carbon gets the nucleophile, breaks the double bond, carbon says, take these electrons and shove it, oxygen. And oxygen takes them and says, I wanted them anyway. Why didn't you give them a long time ago? And then oxygen goes away, and then oxygen comes back and says, boo, I'm so sorry, I didn't mean it. Carbon, take me back. And carbon looks at this and says, well, I need a really good leaving group to leave, and I could take you back, but right now maybe I'm perfectly happy. And this is where this will stop. So oxygen says, all right, fine, there's a proton swimming around in solution. I saw it coming over to your house today. So you know what? I'm going to go out to that hydrogen that's out there, and I'm just going to pull over on the side of the road and say, hey, you want to try to make this work? And that hydrogen goes along for the ride, and off it goes into the sunset with the oxygen. Folks, there you go. There's the product. I told you there's no surprises in organic. You learned the mechanism one time. You just need to understand how the reagents work with the mechanism, and you will be able to predict the products every single time. Now, we have a particular type of term that we like to use for this product. So, in other words, before, prior, we had carbon with an OH and a OH, right? So these two OH groups onto the carbon were called gem-diols. Whee! There you go, gem-diols. Well, we also have a special term for this, and we call this a hemi. Okay, well, it's a hemi what? There's got to be something else with it. It's just not a hemi engine, okay? So it's a hemi something. Well, in this case, let's say that this was an aldehyde. So we can call this a hemiacetal for aldehyde. And if it's a ketone, we could call this a hemiketal for a ketone. What this basically does is we see hemi, and I need you to kind of think of half in a way. So half is the OH, not gem-diols or Gemini twins. That's not two OHs onto the same carbon. We have an OH, and then we have this O, but it's not an H. There's an alkyl group that's coming along with that second oxygen. So hemi, and then acetal for the aldehyde version, and ketal, meaning that it came from the ketone version. Well, we can take this another step further. We can actually take this product and we could react it with CH3OH and H plus again for round number 2. And if we do that, what we can do is that proton protonates the alcohol group. So again, the basics of the very beginning of the semester is still holding true, folks. So here I'm going to write R or H, either one. R on the other side, so aldehyde or ketone again, and we have an OCH3 group that has already been added on. So this was my kind of reagent from step number 1, right? So in this step, if we react it with an alcohol for a second round, you need to think of alcohol reactions. Go back to the very first lecture module of the semester. I told you it will always haunt you in organic. That's just the way that it is. So this hydrogen will go on and it will protonate the OH group, and we have a protonated alcohol group, which is a very good leaving group, and that leaving group is ugly and nasty, and it's treated carbon really, really bad. And then we come around and hit it with CH3OH. Once more, think of this as the hydrogen source, and we have a incoming nucleophile that begins to happen. So what goes on is that carbon gets fed up. And carbon says, you know what? I try to give you a second choice oxygen, and you didn't want anything to do with it. And now you went out, and now you got another hydrogen, and you're trying to bring it home. So oxygen, you have got to go. You are ugly, nasty person. So oxygen takes its 2 hydrogens, and it turns into a very good leaving group. But before it leaves, there is a incoming OCH3 group from that second alcohol addition. This other person comes along and says, hey, carbon, you're looking for a fourth? I could be that fourth if you can kick one of these to the curb. And oxygen says, of course, absolutely, because this oxygen's just treated me nasty. So breaks the bond. That oxygen goes away with the 2 hydrogens, and it makes water, and bye-bye water. So what we end up with now is a carbon with 2 OCH3 groups onto it. Now, once more, this really depends on what we have, a ketone or an aldehyde. And if it goes through this second step, this is step number 2, addition number 2. If it goes through this second step, folks, what we end up with are not hemiacetals or hemiketals. What we end up with here is just a full-blown acetal if it's from an aldehyde, and a ketal if it's from a ketone. So once again, a different nomenclature, different kind of word. Learn your vocabulary. It's all about the words. Acetal, ketal, coming from aldehyde, ketone, and that came from hemiacetals and hemiketals, and that came from actual aldehydes or ketones with the reaction of alcohols. All right, so these are some of the most common organic reactions, especially in the food chemistry world, folks, because a lot of times acetals and ketals and the hemi versions of them, we are talking about sugars, and we're talking about any type of maybe cellulose compound as well. So these are very, very common. They do have a purpose. I just don't want you to think, oh, we're never going to see this again. And quite honestly, you might never ever see it again. But if you are going into the field and you're going to go work in a laboratory, or you're having a science or a chemistry major for that related purpose, this, these are very, very common depending on the type of laboratory that you might find yourself working in, if that's your planned route or career goal. All right. Now, we can talk about mechanism, and you know how I feel about mechanisms. Sometimes I really like them, and sometimes I hate them, and in this case, I do not want you to memorize the mechanism or the formation of the acetals or the ketals. You know, I think what we do is a pretty good job. It's not by textbook, and I think sometimes we don't need to do it by textbook. I think the ultimate goal is just to figure out the ending to these reactions. And what you're seeing here are the curvy arrow mechanisms for the acetal or ketal formation. I at least want to go through them. I at least want to talk about them a little bit. So here is the H and the B, and this H you've got to think as maybe the acid that we have thrown into the mix to initiate this process up. So that hydrogen is actually going to attack the oxygen first as far as the mechanism is concerned. So it's a little bit backward than how we explain it maybe in lecture, at least for me. But it gives you kind of another alternative version of what can go on in the mechanism. So the hydrogen from the acid protonates the oxygen first. That oxygen says, okay, I've got too many bonds. I'm going to break this double bond. And that's okay because carbon's getting attacked with this nucleophile kind of at the same time. So this is perfectly okay for carbon. And we see the addition of the nucleophile that gets added on. Well, just like in chemistry 252, the entire alcohol molecule goes on first. So here we see a protonated oxygen that has been attached to the carbon. This carbon has broken the double bond, shoved those electrons up to that oxygen in order to form the OH group that is there. Now, the nucleophile has to take care of itself. It's not really into a position where it feels really good right now, and that's because oxygen has too many bonds. It has a bond to hydrogen, it's got a bond to the alkyl group, and it's got a bond to the carbon. So we need to rely on this base to come back around and look at this hydrogen for the taking, because oxygen needs to get rid of something. So easily disposed hydrogen goes beep beep bye bye, and hydrogen gets sucked off to the molecule by the basically acid that was in there in the beginning, and it regenerates that catalyst all over again. So oxygen takes those electrons from that bond. It's now neutral. This OH group, perfectly okay. There's nothing wrong with it. And this is what we call the hemi versions. And it's a hemiketal because we started with a ketone in the very beginning of the process. All right, so here, the hemiketal, we could kind of stop it if we're careful at this point. But this is generating an acid, and that acid can then go back and attack the OH group because it is an alcohol, and the organic basic reactions of alcohols are still at play. So the acid can basically donate the proton yet again to the OH group. That protonates the OH group, and that forms a very good leaving group of water. Again, just like the beginnings of the semester. So alcohol reactions are at play. So now what we actually see on this other end is oxygen is getting ready to donate some protons to form a double bond that's here. And that's because the water molecule is getting ready to leave. And that's actually what we see here in this step. So we do see the formation of a carbon double bond O at this point. But when that happens, folks, we see some charge distribution that begins to happen. So there's still alcohol in the reaction, and that alcohol is actually going to react again, just like it did in step 1, where the entire alcohol group goes onto the molecule. It forms a protonated alcohol group. The base rips the hydrogen off one more time, and then we see the OCH3 that comes around. All right, so again, these are 2 steps. We can talk about the top one as step number 1. This is our first addition. And then the bottom piece is step number 2, which is our second addition. So in the first addition, we are adding on 1 alcohol group. which is OCH3, and we form an OH group in the process. That's why we call it hemiketal or hemiacetal. In the second step, water is removed. That frees up a spot on the carbon, and the alcohol goes in for the kill for a second time. And when that happens, we form another O, and in this case CH3 molecule, and that puts that group onto the carbon. So this gives us our ketal in this example because it all started with a ketone, and that is why we use that definition. All right. Now, I also want you to keep in mind, methanol is not the only alcohol that we can use. Any OH group is okay. So, for instance, if this was CH3CH2OH, then what we would have here is a CH2CH3O with the OH on top. It's still called a hemiketal because it started with a ketone, right? And then in the second step, we're adding another CH2CH3OH onto the molecule. So we would end up with a CH2CH3 up here as well in the second round. So it doesn't have to be methanol only. We have an assortment of different alcohols that we could use, and ethanol would work, propanol would work, methanol would work, but quite honestly, they keep it pretty simple. They keep these alcohols very traditional. Ethanol, methanol is typically what they play around with the most, but it is an alcohol-based reaction here. All right. Okay, so that is the formation of what we call hemiketals, hemiacetals, and then going to the full-blown ketal and acetal because of that. Again, I can go through just to do it again, and we can put a hydrogen here, which means that this is a aldehyde that we're starting with. And here, this would be a hydrogen on one of those carbons, which means that this is a hemiacetal because of that. And then in the second step, that carbon still has a hydrogen on it. It just now has the R and the two alcohol groups. And that is called the acetal. All right. So the word is going to give you a name of what was used in the process in the very beginning. Okay, so that's where I'm going to stop with the acetals and the ketals and the hemiacetals and the hemiketals and the ketones and the aldehydes and the reactions with them using alcohol. All right, so like I said before in the previous video, there's just a couple of more reactions to go forward. And folks, we're really looking at two mainly, and that's it. And these two are specialized reactions. So they are named after people, which means there's something special about them. We want to give credit where credit's due, and that's how we're going to finish up this series of reactions of aldehydes and ketones. So in the next step, we are looking at Wolff-Kishner, and that's where we're going to start. So I'll see you in the next video.